Yeah. Unknown Brain, Marvin Divine. I'm saying bye to all the lies and all the times you cried, saying that I wasn't right, yet I was right by your side. You manipulator, playing games, your friends commentators, and I don't know what you say about our private conversations, but it's got them hating. Thanks to all the rumors you be claiming. It's cool, I'm done with you, so they can throw you a celebration. You gon' hate it when you see me with somebody living better. I'm trying to tell you that me just doing me gon' have you jealous.
I know that I gotta stay away from all your games, yeah. I know that I found somebody else to love me one day, yeah. You'll realize the grass ain't greener on the other side, no. You did me dirty for the last time, so now I gotta say goodbye. So now I gotta say
Yeah, my life is lovely now, I'm focused on me. You said you were about to die, I guess the car is on E. But see, I ain't even tripping, cause I just chose to believe that somebody gon' come around and give me just what I need. I don't wanna see you finding, see you looking down and out, coming to me crying, saying you miss having me around. Gave you chances and you blew it, you so easily influenced. All the times you told me beat it, now you gotta face the music. I'm saying
I know that I gotta stay away from all your games, yeah. I know that I found somebody else to love me one day, yeah. You'll realize the grass ain't greener on the other side, no. You did me dirty for the last time, so now I gotta say goodbye.
Hello again. I am back to continue my streak of streaming binary exploitation practice. Hopefully every day this week. Did it both days over the weekend, and so let's see if we can get Monday through Friday as well. And figure a daily kind of practice will be my best bet for improving over time. So I will just jump into it. What we're going to be working on in this session, in this stream, is starting off with the Seesaw 2019 challenge named Baby Boy. And if possible, if I go through this one quickly enough, then the Seesaw 2017 qualifiers, which I guess is SVC or service. So might be able to get through 2 of them today if things go really well. One thing I noticed as I was setting up for the stream is this is the first challenge where we are moving into a new category, at least in terms of the naming of the directory that these are organized into. So these are number 8, and it's buffer overflow dynamic. The last couple that we were working on were buffer overflow static. Not sure. Oh, I don't know why that didn't occur to me until just now. It's not about the memory that is being used for the holding something related to a buffer overflow. So it didn't end up being like overflowing memory that was statically allocated or overflowing memory that was dynamically allocated, or will be in this. It's the binary linkage. So the previous 3 challenges, I think Simple Calc, Feed Me, Speedrun, these 3 were all statically linked binaries. And so our ROP approach was to find gadgets and just do a whole ROP chain with gadgets to do our shellcode, because we had so many gadgets from having all of libc, well, not all of libc, but all the relevant pieces that the linker had included for libc, which ends up still being, quite a bit of code. So I'm assuming these 4, I think, that we have remaining will be dynamically linked libraries. We'll see that in a second when I run like file command and all that. And if they are dynamically linked, then what we might want to do is just do like a return to libc kind of attack. So rather than have a ROP chain that we set up, because maybe we won't have enough gadgets, or maybe it's just simpler if we can say like put the return address of the system function, and then maybe one gadget to pop a thing into the right register depending on the calling convention. The system call might require us to have that first parameter in a particular register, or it might require it to be on the stack, in which case it's a little bit simpler because we don't have to pop anything off of the stack. It'll do that for us, but we'll figure it out. So I think that's what the category that we've moved into is about, is let's do the same kinds of stuff, but with a dynamic linked library for our buffer overflow. I'm guessing we're still going to use ROP, so NX is probably on for all of these. We will be able to figure that out as well in just a second. Turn up the microphone a little bit more. Okay, so I've already copied in the file, Baby Boy, and it's 64-bit. It is dynamically linked, as I just occurred to me that would probably be the case, and it is not stripped, which is helpful. And I feel like the sort of statically linked stripped binaries, both of those were from DEF CON qualifiers, so they might just have a higher threshold for annoyance for somebody doing reverse engineering, because it just adds another layer of work to figure out what's going on in the program if you stripped out all of the symbols. Whereas I think a lot of CTF challenges are like, I don't want to make it extra annoying if that's not the point of the challenge. So we'll do checksec on it. We find NX is enabled, so we're going to do ROP. There's no canary, so that'll, we don't have to worry about leaking that or otherwise dealing with it. No PIE, so we should... I don't know if the libraries will be linked in at different addresses every time we run it. We can throw it into GDB after I run it the first time to see what's going on with it. But if like libc is based at a different address every time we run it, then we might have to leak something, or we might have to have a different kind of attack than the what I had just mentioned about like return to the system call or something. Not the system call, sorry, to the system libc function. We'll find out in just a second, but even if we don't have statically based or non-random base for the included libraries, and we can see what those are with LDD. So we've got just libc, and it does give us an address, but like I don't know if LDD would give us an address regardless of where it actually shows up when the program runs with ASLR. So let's say we don't know where libc is at in memory, and we don't have a way to leak it, to leak some kind of pointer to figure that out. We still would know where the baby boy binary is based, because there's no PIE for it. So we could just rely on gadgets that exist in that binary, but there's probably not that many of them. If we look at the size of it, it's 8.5K versus like the speedrun one was 750K. So, we are 2 orders of magnitude smaller basically. And the usable number of gadgets is going to drop significantly, especially if the memory protections are set up so that only the intended instruction segments, so text section basically, whatever segment that goes in, if those are the only executable segments, then we're really limited. We might be looking at like a couple thousand or maybe even just 1,000 or less instructions to work with, which doesn't give us a lot of gadgets probably. So we'll find out. I'm gonna just run the program first. Oh, okay, it leaks an address, so that's probably what we need to do. It's the same address every time, so that's interesting. Oh no, it's not the same address. I was just looking at the end. So there's a little bit of, it is going to be based somewhere else, but that's fine. We want to figure out what this address is. Is it the address of the system function? That would be ideal. If it is not, then maybe it's an address of something else in the libc library. Fine, good. It's very unlikely that it is the base address of the libc library text executable segment, wherever that's been mapped in. The reason that that's kind of unlikely is I would imagine that those get mapped in on page boundaries, and this is not the start of a page boundary. I think you'd have like 4 zeros or something for like a 4K page. Maybe it's 5 zeros, but yeah, so it's the start of somewhere that is, I'm guessing in libc, but we don't know for sure. We can run it in GDB, and this will pretty quickly tell us what we need to do. Okay. Or it will tell us what we can just like look at the memory maps, look at the address that it has printed out for us, and figure it out. So I'm going to run it. It's going to wait for input. I'm going to Control C, and then, so this is our address here, because I can copy that. And then I'm going to run the VM map command, which will print out all of the memory maps for what has been loaded. And if we just paste in that address, we can start looking through. So we're looking for 7A 48 stuff. So 7.9 and then 7B. So it's prior to the 7B one. It's in this area. Or is it? Because yeah, because this ends at 7BC. So it's in this memory mapped segment from the libc SO file, and that is a read and execute. So this is the executable segment of this in Python, why not? Yeah, so this is like an address within the executable segment of libc, and it's going to be most likely a fixed offset from, whoops, put that in the wrong window, from the beginning of that segment. So let me state that again, because I'm like trying to type and talk and I'm really bad at that. This address that it has printed out for us is going to be a different address every time we run the program, but that's because it is some distance away from this address, the start of that memory segment. And if we run the program a couple times and basically subtract this address from the address that it gave us from the address that is the beginning of that segment, we will get a certain number. That is the offset of the address it printed. Whatever it decided to tell us, it gives us an offset into that segment. So it's 413,000 bytes into that libc segment that's executable. Now, if we run the program again and Control C and VM map again, we can do that same calculation. And notice, no, the numbers are the same. So, that's because I am running it in GDB which turns off ASLR. So I'm not going to be able to demonstrate this as easily as I would like. So I'm probably not going to go into the demonstration. But imagine if this were 7B 48 E80, then the base address that we would see in the VM map would be, what are we looking at? Yeah, would be like this instead. So it would, if it was one higher on this hex digit, then it would also be one higher on that same hex digit for the base address, or two higher, or high, like a different value. It'd be the same difference in each of those numbers. which then means that it's the same, the difference between the different numbers, the pairs of numbers. I realize I'm probably just not explaining this very well, so I'm going to move on, but the key thing that we're looking at is this 41,000 is going to be the same every single time we run the program. Even though the address that gets printed out when we run the program on the terminal, at least, is different every time, the 41,000 that we have calculated will be the same, and we're going to make use of that because we want to find the beginning of the libc segment and then also find where the system function is located inside of the libc segment. So whatever this pointer is, maybe it is the pointer to the system function. I don't know. But if it's not, we can use this number, this fixed 413,000, to get to the beginning of that segment, and then figure out a different number to get from the beginning of the segment to the system function. So we have everything we need to be able to calculate the address of the system function and then return to it. But we might need to do a little more legwork to get there. I'm going to take a break for a minute or two. I realize I've just started the stream, but need to take care of something. So when we get back, I will work on figuring out where that system function is, and figure out the offset. Basically calculate this number, but instead of for the address it prints us, I will figure out what the relevant number is for the system function, and then we really do have everything we need to run create the Python Pwn tools exploit and get we might need to do like one or two things to get a ROP gadget, but I think I can get this one done in the next, 10 or 20 minutes, let's say, when I come back. So thank you to whoever's just joined. I'm going to take a break for maybe 5 minutes, and then I'll be right back.
I know the sadness that cripples you. It comes in waves and out of the blue. But there are days you feel freedom too. Bask in the glorious lightning. Move like the sunlight, darkness can't hold you here. Bold and bright, push through the atmosphere. This is your dawn, this is your break. Move like the sunlight, darkness can't hold you here. Bold and bright, push through the atmosphere. This is your dawn, this is your break. Move like the radiate, radiate, radiate. Gravitate, gravitate, gravitate. Innovate, innovate, innovate. Move like the sunlight.
hurt me, you did, several times. It hurts to admit that we're no different. I find it hard to commit, but you don't even try. Still I'm better with than without you. Oh, I'm on it, I want it, but why do you seem to call it your eyes? I can't tell if you're here or you're out there. Do you wanna be out there? You don't need to be Prince Charming to me. I just need this to be real. I don't need no fairy tale. You don't need to kill a dragon for me. Ooh, I don't need no fairy tale. We run and go still every time. Whatever it is, I keep on trying. 'Cause it ain't hard to forgive when you know what it's like. That's why I'm better with than without you. Oh, I'm on it, I want it, but why do you seem to call it your eyes? I can't tell if you're here or you're out there. Do you wanna be out there? You don't need to be Prince Charming to me. I just need this to be real. I don't need no fairy tale.
Alright, I'm back. Just turning off the music on my end. And yeah, let's get right into it. So if I run this in GDB, can I just ask GDB where libc system is? That's interesting. Yeah, so it knows where libc system shows up, and maybe that's all I need. Subtract this address from it. Nope, because that's at a higher address. Oh, because I need it to be 9E. Oops. Because this was not the original address. That was the one that I had modified. Okay, so again, the offset into the libc text segment executable memory mapped region that we have from the pointer that is given to us is 413,312, and then the offset into the same segment for the system function underscore libc underscore system, which looks correct to me because then it ends up calling the do system function, which I know is sort of where the real implementation of that exists. That lives at offset 324,672. So now, if I calculate the difference of those, we have a difference of 88,640 bytes. So all I need to do is take the pointer that has been given to us, subtract 88,640 from it, and that will give us the pointer to the system function. So then I can include that in my buffer overflow, and we can return into the system function. What I see here is that we most likely need to put the string that will be used for the system call into the RDI register. And yeah, so we'll need a gadget for that. So gonna get as many gadgets as I can out of there. What did I do wrong? No, I always call it job. Oops. It's no job. Alright, it's only 43 gadgets. Let's see if we got lucky. Got something interesting. So we do have a pop RDI. So we could pop there. Do we have a way to write anywhere? Because let's see. So I want to grep for dword pointer, or I guess something pointer. I mean, if we have to use byte pointer, this one's not gonna. These aren't gonna work. These are like the 0 values. But yeah, if we grep for that, then we see that we have a we have an OR, and then it adds RCX. Adds 2 RCX. I don't know if that matters. So what I'm trying to figure out right now is, oh, you know what? Where can I? Oh, I can do ROP gadget strings, I think. Or string. Is it? Oh, I need to say dash binary for that as well. Okay. I suppose I don't need the full. Really? There's no SH string. Can I? Okay. What is memster? Not helpful, I think. So my original thinking was, well, can I write the string /bin/sh into memory at an address that I select so that I know what the address is? I didn't find that, but I didn't find the gadgets to do that easily. Maybe like this OR one could be purposed for that, but I don't want to have to deal with some of the other stuff that's going on with it. And frankly, like, I mean, the OR is not necessarily ideal. I guess if you OR to make sure it's 0 and then you OR the bits for the thing, like that's the same as move ultimately, just a couple steps. But I'm not going to go that route, I think, if I don't have to. So instead, is there a string that already exists in memory that I can figure out the right address for? And that's why I was looking on this string thing. I did not find even an SH string in the baby boy binary itself. There's most likely an SH. I can run strings on it. some grep for like. So we have that. I don't know if that'll be loaded, the .gnu.hash, because that's like probably part of the I think that's most likely part of the like elf header, which doesn't necessarily get mapped into memory, if I recall correctly. Do we need see? Yeah. So we've got this stuff, and these are like the names of all of the sections that are in the binary. And .gnu.hash is one of the section names, but I don't know if these section names actually show up at runtime in, you know, a meaningful, like in a place that I could find. I can run it in GDB again, and we can see if the memory includes that, I guess. So if you look at VM map, we have read execute on this first one, and this is definitely the text segment. It's not going to be the binary itself. Can I... Let's see. I wonder if there is a feature in Jeff that will allow me to search for that string in memory, or if there's just a straight up GDB feature. And then, yeah, so I can search, and really the only segment that I'm going to know the only segments I'll know the addresses of are these four. And I think my search with ROP gadget already took care of these first three, because I said search through the baby boy binary. So let's start by searching through this one. So we do find, and I think the syntax was the beginning, the end, and then the string to search for. So that's okay with me. If we don't find it in here, I will. I'm gonna. Doesn't actually. Okay. Can I put it like this? Does that help? Hey, okay, we've got something. And what do we do? Examine string, I guess. And so there is a string starting at that offset, which is just sh and then a null byte. There's almost certainly no bin sh. Yeah. Okay. So, but I think given that system is going to, it's not like execve where it has no concept of the path. System will look on the path, I guess. We'll find out if it works or not, because I don't necessarily have a good way to construct the full /bin/sh path. Maybe if I am forced to, I could work out some way to do it, but it doesn't seem very obvious right now. So we're going to take the address of that string, which we know is in the same segment as the other things that we were looking at. So I'll just take the same base address for it. And now this is the offset for our string for our sh string. And we can take this number and then the offset that represents the pointer that we found, and this is the value that we need to add to whatever pointer we get in order to, I don't want to do this one as well, because it's just keep it all in hex when I write the Python code. So we will add this to the pointer, and that'll give us the address of the, oh, that's going to be interesting. Oh, no, that's fine. Okay, yeah, because we're just doing this, and we're just doing it with a wrap chain. I thought we maybe had to construct shellcode with this immediate value, but that is not, it's not the context we're in at all. So we will have this on the stack. We'll do the pop into RDI gadget, and then we will have this be the return pointer that we go to after popping the address into RDI. So it's not actually going to be this number. It's going to be whatever pointer we are presented with plus this number. And then for this one, it's actually whatever pointer we're presented with minus this number. Okay, I think we have everything we need to write the actual exploit. So let's see if we can get this going. And we need to see target dot receive until colon space, and then I'll say the given address is convert an integer of target dot receive line in as 16-bit, or as base 16 rather. So now we know what the address is. Let's go ahead and just print that out. Make sure that I am doing the right thing for this bit of the exploit. I think so. I guess I could say print it as hex. And yeah, that looks like, I mean, you know, I'm not actually printing out what was directly presented from the binary or from the program itself in order to double check, but these look like addresses that are accurate to what we want to use. So now we have like, let's see, system offset is going to be negative 0x15a40, and sh offset is going to be positive 14d081. And so our wrap chain and there's a few things we need to do first, right? We need to figure out where the actual buffer overflow happens and at what point we get our seg fault from overflowing. So 1024 does it. What about 512? That'll do it as well. 256, yeah. 128, yeah. 64, still very small buffer, I guess. Or very small, like intended buffer. So it's between 32 and 64. So 48 does do it. What about just 40? That'll also do it. 33? No? Okay. 36? Nope. 37? 38? Interesting. Is it 40? Okay, so after 40, we hit a seg fault. So I'm guessing that we need to, maybe we need 48. Thinking back, like, basically I'm trying to avoid popping this open in Radar or something, or even just the disassembler in GDB, in order to work out where exactly the return pointer is going to be in the input that we send in. So remembering what I worked on yesterday, we had a buffer where the program seg faulted if we wrote more than 1024, or I guess including 1024, and the buffer itself was 1024, but we needed an additional 8 from there to get past the EBP that was pushed on the stack. So I'm going to add an additional 8 to this as well, and then we'll see. And we need the pop RDI in from gadgets as well. Okay, so let's do payload is equal to A times 48. And we'll add our ROP chain after this. Go ahead and use this address. Oops. And then what we are popping into RDI is, where are we? Where do we have it? Given adder plus sh offset. And then we are going to just throw the system offset in there as well. That should be enough. Gotta encode this as bytes. And if we add to the payload P64 of that entry value, then we're good, and we can say target.sendLine payload. Let's see. I don't think this is going to work, but, you know, fingers crossed anyways. No. Okay. So I didn't quite figure it out blind. We can try it with 40 instead, but I don't think that's going to go either. So let's run it with, can I run it with GDB? I think what I'm going to do is I'll run it in GDB, and no, I'm going to just do it in Radar, because it'll be a little easier to find the stuff that I'm looking for when it does its analysis. Okay, and then it calls gets with a buffer that is at 20 hex, so it's actually 32 byte buffer. So why doesn't that work when I did it as 40 instead? So if we have a 32 byte buffer, which is what we are doing the gets into, is that accurate? Yeah. we also have another 8 bytes for RBP. And then after that, we should write the return pointer. So what am I missing here? Because then 32 plus 8 is 40. So A times 40 gives us enough bytes. Although it was when we wrote 40, yeah, because there was probably one additional byte that was the new line, and that's what was hitting into the return pointer and causing the crash. We can double check that in GDB. I just copy all of this as our input. So we get a crash in start main. Oh, I didn't put a breakpoint on. So before we do the ret, what we're pointing to at the top of the stack is this address. Oh, I guess it's not necessarily the new line, but it is a null byte. Pretty sure. I think the zeros here are indicating that we have like overwritten what was originally there. So if I run the program again and we paste that in, but I take off one of the A's, we can see it is not a null byte here, it's a 97. 05B00 versus 05B97. So this one is going to complete correctly. So after 40 A's, we should be overwriting into the return pointer. So what has gone wrong? I don't know. But what I can do is generate a version of this payload where I'm not actually going to interact with the target at this point, and I'm going to say given adder is equal to this fixed address that GDB is giving us. So then I can print out that payload. I think that's all we need. And we've got all of our A's and then stuff for the addresses that I am giving. Now, what is that first address? Oh, this is not based correctly. That's the issue. This 40,000 is really more maybe the offset. This is me not using RobGadget correctly, I guess. Okay. Let's see. Can I give an offset? I guess. We'll see if that does what we want. And we will need to find that from VM map. So this will be our offset, I guess. This 40009307. 4000. Or, oh, I'm probably reading this wrong. It's 4093. So that should actually be based correctly, I think. Well, let's try it in GDB with our input, actually. So we'll put in the breakpoint for the return address, and then we'll run it with exploit.txt as the input. So now the location that we're returning to is our pop RDI gadget. So if we run that, what are we going to pop into RDI? Pointer to the string sh. Sounds good to me. We'll return from that, and that returns us into system. And oh, is this the stack alignment issue? So if we continue, where is the seg fault that we get? Why did we end up here? What is RIP? Yeah, like RIP ends up in a completely wrong place. How does that happen? I don't think so. All right, we'll run it again. So we go into do system. R12 has our address, our pointer to the sh string. And we're just gonna keep going through all of this stuff. What is in racks? We just zeroing stuff out? Okay. I don't know anything about what goes on in. Okay, so we just did a syscall, but I don't think that's not the like exec VE syscall. So again, we aren't getting a seg fault in my, oh, okay, let's see. We returned from the call to system. So maybe it does not run like maybe we need to pass in /bin/sh, and the reason that the system call is finishing. Oh, well, the shell might be ending because we don't have additional input for it. And I haven't provided that input. Even though, like, in our Pwn Tools exploit, we do call interactive on it, which I would think means that So if we call interactive, then we aren't going to run out of input and close the shell right away. That won't be the case with our exploit.txt. So I guess what I could also do is say, write a new line and oh yeah, I guess I didn't actually write a new line at the end of this, so I need to do that as well in order for gets to be able to do other stuff. I'll just call ID. So let's try it this way. What? Okay, and then we'll run it in GDB again. Put the breakpoint on there. And run it with our exploit.txt. Still get to system, so if we continue from here, and we still return to, you know, an invalid address. I guess we could, no, because I bet libc start main is not in. Well, let's try and run it as usual. And then we're going to return to this address, which is 7A0. You know, that should be an acceptable address based on just going to throw that in there for the purposes of our GDB like test exploit. This is like this is the instruction that we would normally return to in the main function. So if we also have that on the stack, maybe it'll be available for when system returns, but I mean, we're not really solving the problem that we have, I think. So this is probably just not the way to go. Actually, I don't know why. Yeah, okay, so that definitely exited when it was done, but maybe it didn't. Oh, so it is the stack alignment issue. Okay. So this issue I ran into on some of the earlier ones, and it's really due to the particular system that we were on, Ubuntu 18.04. You know, maybe later Ubuntu versions as well. Maybe other distros for Linux have this issue. But the way that the libc gets compiled, it uses this move APS instruction, which will segfault if your stack pointer is not aligned to, I think, 8 bytes or maybe 16 bytes. So our stack pointer right now is this. I think it needs to be offset by another 8 bytes. So we need to push something to the stack or pop another thing from the stack. Let's see if I can We really don't have any push gadgets? We don't have any push gadgets. Okay. But we do have an add RSP8. So why don't we do that? And that should be enough. We need to insert some stuff into our ROP chain. Oops. Okay, so we don't want this anymore, but we do need to have a ROP gadget for updating RSP so that it is aligned properly. And when we add to it, so when we get into this gadget, the stack pointer would point here, and then we're going to add 8 to it, which is going to make it point to this line, like the line following it. So I need to just insert 0 so that when we add 8 to it and do the ret, it's actually pointing here still. Okay, let's see if that does it for us. No, damn it. Maybe my thinking on that is incorrect. We'll find out. So we'll generate the exploit.txt again, run it in GDB. I'm gonna set the file fork mode, and I'm gonna break on returning from the main function, and then run it with our exploit input. So right now, stack pointer is, why do I always lose it in here? It's aligned on an 8-bit boundary, which is interesting. It's not, or an 8-byte. It's not 16-byte aligned. So I don't know why that is, but that's not my doing. Then if we go again, stack pointer is aligned on 16. Now we're back to 8 alignment. Do we need to do it twice? Maybe we need to pop more than one register in a given gadget is how we would do it. Just pop 2 things. Because I think if I just continue from here, we're still getting to this point, and RSP is still 8-byte aligned by the time we get to this instruction. So even though I had something which added 8 to RSP, the issue is really that we add 8 and then we ret, which adds another 8, so it doesn't impact our alignment. So if we do 2 pops, each pop will add 8, and this will result in hopefully the stack being different, differently aligned than it was before. I need to get into Vim. Okay, so we want this one instead. So let's do this stuff. Setup. Set up the parameter to system. We don't need that. We'll do the call to system. And then this will align the stack for us. Okay. And now it works. Sweet. Okay, that took a bit longer than I anticipated, but I mean, I think I had it pretty much on the 48 was wrong. It was just 40 that I needed to hit. But otherwise, from there on out, I had it except for the issue of the alignment thing, which, I mean, obviously it's part of what you need to get working in order for a real exploit to happen. But it's pretty system specific, so if I were running this on a different version of Linux, or certainly an earlier version of Ubuntu, but maybe a different distro as well, then maybe I wouldn't need to do any of that work, and it would have saved myself 15 minutes, 20 minutes, half an hour, however long it took additional to get that going. So the lesson is, on this particular machine that I have set up, I really need to remember about the alignment issue and check for that if I'm getting a seg fault before assuming that it's some other issue. I've got my ID, I'm still Charles because it's not a SUID binary, but that is fine. So yeah, we got the exploit for this one. Okay. I feel pretty decent about that one. I am not going to go through the walkthrough. Okay. I will read this after the stream, maybe. Actually, this one is really short. Let me read through the walkthrough because they did it a different way. They didn't make a constructor ROP chain by hand. So let's see. Let's look at the binary libc file and source code for this challenge. We do get a copy of it. Oh, well, that might have saved me a tiny bit of time. I didn't notice that we had the source code. So they tell us it's 32-byte buffer. Then we add the 8 for moving past RSP. That's all good. One issue with challenges opponable where they give you the source code, and in particular if they give you the source code and not the binary, is you don't necessarily know what settings were used to compile it, and that has a dramatic impact on what exploits are possible, because maybe they compiled it with PIE on, and then what we're doing with the ROP gadgets doesn't work because we aren't leaking an address for the baby boy binary. Although we're still leaking the address for libc, so we could look for ROP gadgets that are in libc. We would have to do that dynamically, roughly. We could probably use ROP gadget to find them with an offset of 0 and then add them to the pointer that we work out for the base of libc at runtime, rather than have to actually run the ROP gadget finding process at runtime. But set that aside. It would be a different technique if we had PIE enabled. Okay, so they look at it in file, they run checksec on it, they just run the libc library file, and then it prints out like a standard copyright and version info. Then they run the program, and then they look at the source code. Okay. So we can see that the binary just prompts us for text. Looking at the source code, we see that it prints the libc address for printf. After that, it calls gets on a fixed size buffer, which gives us a buffer overflow. We can see that the libc version is libc-2.27-so. Also, the only binary protection we see is NX. Exploitation. So this is where I just very quickly noticed they were doing something different than how I went about it. So let's see if there's any improvements that can be made to the technique I used, which was really manually constructing a ROP chain. So to exploit this, we will use the buffer overflow. We will call a one-shot gadget, which is a single ROP gadget in the libc that will call exec/ve/bin/sh. Oh, that's very convenient, given the right conditions. We can find this using the one gadget utility. Interesting. Like, why would there be such a gadget? I guess within the system call function, there has to be a part that sets up and runs exec-ve. So we are just leveraging the internals of the system call as our gadget. And the way that system call works inside of like the do system function, I'm assuming it's inside of do system, but it might be some other internal bit. The way it must work is it pops the string in like from the stack into the appropriate first parameter register for the system call. Maybe it pops another thing, or it just straight up refers to a stack address for the like arguments piece, and then points at the known location of the environment. So we don't pass null for the environment, we use the real environment, which is fine. So leveraging the libc info leak with the printf statement to the libc printf. Okay. I think they're saying the leak where they print out the address of the libc printf function, and that we know which libc version it is. We know the address space of the libc for which one gadget to pick. I typically just do trial and error to see what conditions will work. You can actually check when it is called to see what conditions will be met, however. Okay. I need to read through that repo, I guess, to understand more about what they mean by gadget, or conditions rather. So exploit, putting it all together, we have the following exploit. Their thing figures out. Okay, so they use pwn tools, I guess, to set up the basically parse the libc binary and figure out the offset to know the base. So they statically determine the address of printf within the libc binary, and then use that combined with the leaked address to figure out the base of the libc executable segment and add that to where their gadget goes, or exists rather. Kind of the same as what we did. I just ran it in GDB to figure out the offsets and stuff. So it's good to know that we could also do that in Pwn Tools, just load it as an ELF file and then ask for a particular symbol that is not exported, because that's like Windows terminology, but a symbol that is included because you need that symbol in order for the linking to work. So we know that like libc is always going to have printf, it's always going to have system other stuff, etc. Okay, maybe I'll try that next time on the next challenge that I do, which I'm going to try to go for one right now because this went pretty quickly. Try to get the next seesaw one going, and yeah, then they run their one gadget, which is pretty interesting. Okay, so let's real quick take a detour and look at finding a one gadget RCE in libc SO6. And I'll go ahead and hit a star on that because if it does what it says, and what it says it does is pretty neat, I think. When playing CTF Pwn challenges, we usually need the one gadget RCE, which leads to call. So they say they usually need it. I haven't needed it before, but certainly if you are space constrained, if you do not have sufficient space on the stack that you can overwrite to do more than basically one gadget. In fact, yeah, if you can't overwrite beyond the return pointer at all, then you need a one gadget kind of thing. So I think I will try this from here on out. What is the one project it's used by? Pwn Tools Ruby. Interesting. Oh, somebody ported Pwn Tools to Ruby. That's nice. Oh, because this is a Ruby project. Okay. Because we're installing it with Gem. Yeah, I want to read their blog post about how they developed this, because I don't understand how such a gadget exists. Maybe. Oh, because, okay, right. The way that the system call works is it really exec VEs the /bin/sh binary, and whatever you pass in to system is, I think it passes in a -c string, and then the second string is the command that you passed to the system function. So this is like, we've already got a piece in libc that is just run a shell, because that's what the system command effectively is doing, is run a command on the shell. So okay, fair enough. Let's see if I have it already. I don't see any reason I would. Do I have Gem? No. Okay. So, oh yeah, I still need a sudo. We can install Ruby, and then I can globally install just one _ gadget, I think. Yeah. Okay. Maybe I'll need to put that on the path somehow. We'll find out. Nope. Okay. And now we have it. Okay, sweet. So I can use that on the next one, and maybe just generally going forward for any of the dynamic ones, at least, where we have libc linked in. It just gives us the ROP gadget that we need to do everything. So I'm not going to read through the whole blog post to begin with, but what I would suggest is, search for one gadget on GitHub and it'll link to this page, or if you can read this URL. I don't know how I can easily make it larger font. So if you can see this on the stream, check out this URL or just search on Google for one gadget, the one gadget in glibc. And yeah, I will read this after the stream, but I feel like I know how to use the tool just from seeing them do it in the walkthrough. We give it the version, or we give it the name of the libc binary, like shared object to work with. So, okay. On to the next challenge. We're going to, what did I do? Copy the wrong thing. Nope, I don't want the index part. All right, so this one is Seesaw Quals from 2017 service. And all right, so we've copied in the service binary, and looking at it, it's a 64-bit ELF, dynamically linked, of course, because we're in the dynamic section of challenges. But this one is stripped, so oh well. And if we look at it in LDD, this is a C++ binary because we're linked to lib standard C++. So that's the C++ standard library. Don't remember if that's Clang's one or if that's the GCC one, or the GNU version of the C++ standard library. They have names that are similar enough that I can never remember which one is which. So I don't think it'll matter. We're linked to libc and libm for math and libgcc. So probably it was built with GCC, and maybe this is linked as the GCC variant of the C++ standard library. Again, don't think that stuff is going to matter too much. It's going to maybe make the reverse engineering work a little bit more annoying, just because, if it's using a lot of templated code, that tends to result in a bunch of tiny little functions rather than something that's a little more straightforward if it was written in C when you are looking at it as assembly code. But before we get into all of that, we'll just run it. And SCV, so that's interesting. They named the binary SVC, but when we run it, it talks about SCV, and I feel like SCV is one of those StarCraft, the Terran, the little worker guys that'll mine and build and all of that. Space construction vehicle. Okay. And that's one of their quotes, right? SCV, good to go, sir, I think. So we can feed it, we can review the food, and we can mine minerals. Hello. Okay. So I think we can put in a string, and then we can replace that string, and then 3 is just quit. So if we so trying to find where the overflow exists, if we hit 1, enter, and then try to overflow on this input, we can do should, whatever. Oh no, what did I... Do not hurt my SCV. Oh, did I not run checksec on it? I don't think I did. Canary was found. So maybe we are hitting a stack canary in trying to do the overflow. So let's say we have a buffer that's like 10. No? Why did that... Because this should just like... Yeah, I don't see in what way... Oops. Well, I don't know why it's looping forever with this set of input. Unless it really is a very short buffer. No? Okay. So, say 1, and then we enter A, and then 3. So all I've done is say 1, new line, A, new line, 3, new line. So we echo 1, and then A, 3. It loops forever for some reason. Don't understand that. Don't understand that at all. What am I doing wrong here? Well, let's give it a shot with just doing the overflow manually. Start with a big amount of A's. What did I... Oh, I think I just typed that quote there. Okay. Oh, geez. Okay. So that triggered the... whatchamacallit? Trigger the stack canary check, I believe. That's probably what the do not hurt my SCV input or output is about. That also did at 512. Try 256. Yep, okay. I don't know why, I mean, I know why I start with such large buffers, large inputs to begin with, because I've seen ones where the challenge has a buffer that's like 1024. So 128 was fine. Although we can see it starts maybe overflowing into something because the output that we get is not the same as the input. There is no whatever this symbol is supposed to represent in actual binary. So let's try to, well, that's just adding 4, right? 136. And so another 8 A's, another 8 bytes doesn't seem to impact on it. Interestingly, it, reads fewer bytes than we typed in. Yeah, I have no idea what the logic is on why this one seemed to wrap around or has a new line, I guess. And then this one does not, but it is shorter than the input that I gave. But we haven't triggered the overflow yet. Or at least we haven't triggered the canary yet. That one is still fine. We are again getting some amount of like corruption coming out of that. So keep trying to add more bytes. Okay, more corruption. When we're at 160, do we hit the canary? Nope. So I don't know why I've switched away from doing what am I trying to say? From doing like a binary search. So I should have just gone to 196 if we're trying to find where the canary comes into play. So wasn't at 196. So what is 32 plus 196? It's going to be 228. Does that make sense? Plus another 30. That would be 26. No. So we need... Wow, how am I this bad at math? Oh, maybe I just did... Maybe 196 is not the number that I need to be using. So I was trying to split the difference between 128 and 256. 256 minus 64 should be 192. 192 plus 32 is going to be 224. That still doesn't bother it. Okay, and then add 16 to this. It's going to be 240. Nope, doesn't trigger any kind of canary. Although, what the hell is that? Maybe the canary is not what I think it is. Oh, that's interesting. Okay, so it just loops forever if you hit end of input, which, I don't know, maybe that's simply poor programming on their part, or maybe that's intentional. But if I type in 1, basically give it no text, and then hit enter, we get something printed out. So that is curious for sure. Okay, but then if we go to 248, it's also fine with that. And we do get some corruption immediately following, not even following, I think. Oh yeah, because there's the 2 brackets. 2 greater than symbols. So I think like there might be 8 bytes worth of stuff here, but maybe one of them was null byte and that's why it ends. But that could be where we are running into other stuff on the stack. Oh, and it did, and stack smashing was detected at that point. Okay, interesting. And yeah, it's a different value each time. Okay. Now, if I do this, let me see, this is like percent other stuff is what gets printed out for that particular I didn't enter any text scenario. And now if I give it this thing and look at it, it is not percent stuff. Okay, so my guess is the reason that we're in this loop and we have the ability to give it some text and then see what the output of that text is and give it more text is that's the mechanism by which to leak something. I don't know if it is leaking the stack canary or leaking some other useful piece of information, but that is my guess. I mean, I would say if we're dynamically linking to libc and we have ASLR on, then we need to link a libc address somehow. Oops. I always forget that hitting Control D is just gonna spam it. Let's look at security again. So no PIE, NX is enabled, so we're definitely doing the ROP thing again. Whether it's the one gadget, if we can do that, if we have a libc address or not. And we can also use stuff from the actual SVC binary, which is 11 kilobytes. So again, very small. Not nearly as small as the earlier one because it has all of this logic, whereas the other one was literally like print a thing and then call gets and you're done. So I think I really do just have to go in and start looking at this in Radar because I don't know enough about the buffers that are being used and what else is on the stack and you know what the data is that's being represented in this corrupted, you know, not corrupted memory, but we are reading beyond the memory that we have access to on the stack, or we're reading beyond the buffer that we should be writing to. So let's open it up in Radar. Do we have a main? We do. Okay. So yeah, this is another aspect of using C++, is it's going to have these ridiculously long function names because of all the template parameters. This is printing out the menu and then receiving the input and converting it to an integer. So let's see, I think BC is the location where we have stored the menu choice, and that's what we're comparing against to. If we selected 2, then it is going to, where are we? Oh yeah, okay. Right, this is the, I mean, I was just tripped up by how much printing is happening, but I think that is actually just what it does print. So we have this as the thing that is printed. No, this is the, I need to just run it here, I guess. There's so much stuff that gets printed out. Okay. So after printing, please treat him well. And then after printing, okay, so this is the location of the buffer that we are printing inside of here at B0. Okay, now if we go up to the top of the function, so that gives us a buffer size because we overflow into the next thing at B8, which is probably the canary. 168 bytes. So when I was giving input that was that large, why was like all of this not triggering stack canary stuff? Maybe it was, and I just wasn't seeing it from the output, from the behavior of the output. So if we do 160, let's say, I say throw in this text and then quit. Oops. No problem with that. I throw this in and do 1, 2, 3, 4, 5, 6, 7, 8. Another 8. It should be okay with this as well, because this should be the full length of the buffer. But no, that... Oh, maybe I didn't hit 1. That's my bad. Okay. Nope, I need to hit 1, paste this in, and then quit. And that was stack smashing. So I guess because it probably calls gets or something and writes as a null byte after that. So if we do 7 instead of 8, that should be fine. Right. So after, if we write 167 characters, then we have filled up the buffer. So I guess this thing could leak us the stack canary, because we could write exactly that amount and then we'd have 3 bytes additional that we could read, and we'd have to put that stuff back in. Thus, I sort of see the idea of see. Oh, hello, Meowcat. Working on more binary exploitation challenges as always. Trying to figure out one where we have this. You fell asleep. I guess it's what time? Like, what about time is it over there? Because it's only 11 in the morning here, so just getting started on my day. We have this like stack. How to put it? Oh, I fell asleep during the last stream. Gotcha. Yeah, I mean I understand. Why did I lose the colors sometimes on Radar, and I don't know what I've done to trigger that. we're trying to figure out how to exploit this one, as always, but right now what I can see is we have a buffer that I can overflow, and then immediately after that is a stack canary, which I don't know the value of, but I can print the buffer. So if I overflow it enough to get if it writes a null byte at the end of the stack canary, that is tricky. I need to look at this code again. I'm gonna quit out of radar because I want the colors. Or maybe I can just do this and it'll give me back. Okay. Trying to figure out how I can leak the contents of the stack canary, basically. Because I can write to this buffer and then read it again and then write it fresh. And I think when I read it, I can see the canary if I just write enough bytes to get to it but not overflow it, I suppose, is a good way to put it. Not overflow beyond the canary for sure. But we need to find the code where we actually do the writing, which is going to be this red path. And down here is where we read in a certain amount of data. So we read into the buffer at F0, or sorry, B0, and the amount that we will read in is F8. Okay. And then B4 will have the length of that buffer, or the amount that we read in at least, because that's what comes back from the read function. The return value goes in EAX, and read returns the number of bytes that it read. So maybe it's just going to use... why does that do that? Doesn't all go up there. This function is confusing just in terms of... Okay, yeah, I guess this is the up. And then we come back. So do we use B4 anywhere? Does that actually get checked for anything? Perhaps not. So the way read works is it'll read a certain count of bytes from the file descriptor. And it's not going to read, it's not going to do a null byte or anything. So that's why we were able to start reading the stack canary. Because unlike with like gets, which will always terminate the string that it creates in the buffer, it will always terminate that with a null byte. Read doesn't care because it isn't necessarily reading in a string. Whereas gets, the S stands for string, get string. So that's always going to terminate with the null byte, which prevents us from then printing out data beyond that string in the setup that we have. But we aren't using gets, we're using reads, so we do have that capability. The issue that I need to then figure out is how to get read to be able to read an amount that is how to put it. Basically, we want the read call to finish and not have read F8 bytes. That's too many bytes for us to read. It would be good for now, for later when we need to actually like overflow with a ROP chain and stuff. But for the purposes of reading the stack canary, we need to only write enough bytes so that we get right up to the beginning of the stack canary, which, and maybe one past it, because the first byte in the stack canary little endian setup, I believe, is going to be a null byte by definition, and I think maybe this is part of the reason that they have that as the lower byte in the stack canary is null. In any event, we can't fill up the read buffer and have it read beyond 168 characters, which is like A8 or something. Yeah, A8. But we do need to still have input. We can't just have that be the end of the full input to the program, because we will need to repeat this process. So we need to like make available a certain amount, and I can do this with Pwn Tools, I think. So let's just start writing the exploit. I don't know a lot about what we're going to do for the exploit yet, but we're going to just start writing it. And I think I'll be able to use the send and receive behavior that the process thing from Pwn Tools gives us. So when I set up a target process, I call process, and what do we call this? SVC. And now I can like receive until, I believe it prints that out. And we can send line 1. So this is like choose to write input. So we're selecting something from the menu. So if I call SVC, if I just run the program, it prints all this stuff out, and we're telling Pwn Tools read until we see these two greater than symbols, angle brackets. And it will read all of that, and since we aren't saving the text, it just discards it. And then we're going to send 1 and enter. And now we have selected the first menu option. We will again read until we get to the 2 angle brackets. And now we're going to send a fixed amount of text, which won't have a new line after it. So we're not going to call send line, we're just going to call send. And that fixed amount of text will hopefully allow us to overflow the buffer. Not even overflow the buffer. We are maxing out the buffer, but we're not going to have a null byte at the end of the buffer. Thus, when we read the buffer, we read beyond the end of the buffer. So the sort of, it's not exactly an overflow, it's just a like reading memory out of bounds kind of thing. We'll say target.send, and we will send A times 168, because that is the exact size of the buffer. And then we need to again receive until the prompt. We will receive until the prompt again. We'll say target.send 2. So this will allow us to read the input that we sent, but it will continue reading beyond our buffer and into the stack canary. And need to remember what it looks like when we do the read command. So the read, and I am curious a little bit about like what's going on here. I think this is just garbage from the existing stack. I don't think, I mean, it's not exactly garbage, but it might not be meaningful to what we're attempting to do. On the other hand, it might be a pointer that we can use. I don't know. Because we haven't actually given it any input. And so then we hit 2 and just to read the input buffer, even though we haven't written to it yet, and we've got gibberish in there. So I want to read to I guess, you know, dash, or I can just read 1, 2, 3, 4, 5 lines. Oh, forgot about that. I think maybe we can do that. Let's look at, do I still have the pwnlib stuff open? Yeah. So take me to the receive line. We don't have receive lines with just an S. It allows us to do a fixed number of lines. Okay. So receive 5 lines, and then we will say input equal, or no, let's not call it input. I don't know. Buffer is bad? Okay. Buff is target dot receive until /n and then some number of dashes, because after printing that stuff out, it prints a new line and then starts printing dashes, and we don't care about the stuff after the new line really. And I want to then just print the buffer. And we'll see what that looks like to start with. And that did not work. Still waiting for input, I guess. Okay. I'm going to send some data, but I might need to search around to figure out how to achieve this. Because we need read to complete the read call, but not be done with the input. And not put a new line character in the input? I guess that's a good question. Why doesn't it mean like... maybe this is a libc thing? No, fread is the standard thing. So I need to understand how it knows that the buffer to finish reading. So reading from a terminal, okay. There's some mechanic in here that I don't really understand about how read is able to determine that it is finished reading and it should return back to the program with whatever, having written whatever it has thus far. Because if I run it in the terminal and I type some text in and hit enter, that is a signal that results in read saying, okay, we've read everything, we're done. But if I, how do I put it? But if I'm sending it from Pwn Tools, when I just call send, it's still waiting for additional input, I'm pretty sure. So let's do send line. Oh, I need to say send line here. Maybe that's the issue. Yeah. But then we get the /n. Why do we have the /n there? Okay. Do one more than that. Now we get the stuff from beyond the buffer, I guess. Right, okay, so this makes sense. So if we write 168 bytes, that is the exact size of the buffer. The /n doesn't matter, that gets added by puts when we are printing it back out. So this is the exact amount of stuff that is in the buffer, and it is not overflowing at all. So we do technically need to overflow a little bit. And because we do this, then immediately following it, ignore the /n, but imagine bytes that are following this. The first byte that's in the stack canary is always going to be a null byte, so that counts as the end of the string, so it just reads to there. But if we do one more byte in the read call, it overrides what was in the stack canary, that null byte at the beginning of the stack canary. We put an A there instead. As you can see, if it lines up perfectly, it is the one byte beyond the last A. So we replace that null byte with an A, meaning it's no longer the end of a string, and then we can see the bytes that follow it. And we are most interested in these 3 bytes, because those are the remaining, or I guess not 3 bytes, it's probably 8 bytes, because we're in 64-bit. So we need the next 7 bytes. We know that the first one is going to be 0, even though we've overwritten it. We know that it started as 0. And then we've got an additional 7 bytes, I think. 1, 2, 3, 4, 5, 6, 7. Yeah, and I think it basically ends here. And then maybe this stuff starts being involved in the RSP pointer that was pushed to the stack after. So I'm not going to worry about figuring it out here. We're going to figure it out in the Python code. So we've got our buffer, and we want to identify where the canary is. So the canary is going to be buffer. I think it is just B. Let's do it as, or you know what, receive until is always bytes, right? Oops. Yeah, because we got the B here at the beginning. Okay, so I don't have to worry about that. And what we want to slice out of the buffer, starting at 169, or the 170th character, and then going to the 177th character. We went the 176th. I think we went to 176 because we only need 7 characters. And then let me say B plus that, and we'll do this as byte, and then the canary is actually U64 canary bytes, so we'll unpack that and print the hex of the canary, let's say. Okay, so this is the canary that we have figured out. If we run it again, it should be, it's a random value each time. Okay, so now we know what the canary is. We have been able to leak that because our buffer overflowed enough to let us read into the canary data. And we could reconstruct the null byte that comes at the bottom of it, at the lowest valued byte. So when we write again, did I solve the previous one? Yeah, I was able to get through the speedrun. I mean, I've been doing them all in order. So basically, I've solved all of the ones up through here. Earlier in this stream, I did the baby boy one. I think maybe the stream you were looking at, I was working on the Feed Me challenge. And so I did end up getting that eventually. And yesterday, I did the speedrun one and went really quickly. Maybe that was the one you were talking about. But this one went pretty fast because it is actually just a really straightforward challenge as part of the idea of making it a speedrun kind of thing. So that one took maybe half an hour. But I only had a little bit of time. Had to go to the dentist after that. So I sort of cut it short. I didn't try to continue on and do more challenges. But so far in this stream, I was able to do Baby Boy. That one was maybe 45 minutes to an hour. And a lot of that was, I had actually gotten it basically working, but there was a little hiccup that if you watch this, if you feel like going back to the stream, there was a bit of a hiccup with some like stack alignment issues that I had encountered in previous challenges up here and then forgotten about. And so I was like trying to figure something out and not looking at that, and turned out to be a pretty easy solve once I realized that was the like little hiccup. I call it a hiccup because it wasn't part of the challenge. It's a additional bug that I have to work around. I say bug, but it's an additional thing you have to work around on this particular system running Ubuntu 18.04. If you are running maybe an older version of Ubuntu or something, that wouldn't be a thing you had to work around basically. So it wasn't what I consider the main part of the challenge, but it did end up taking a significant amount of time. And yeah, so I think I will try to get through the SVC one. If I can get this going by, in the next little bit, I might check out Overflow, but I doubt, like, this one is definitely more difficult than Baby Boy. It's building on the same principles, but it's more difficult. So I would expect Overflow to also be more difficult than the one I'm working on right now. So if I start on it on this stream, because I don't think I'm going to be able to stream for like 5 hours or something today, I don't anticipate finishing it. But depending on how quickly I get through this SVC one, which is really should be called SCV for whatever reason. they've called it SVC. In any case, if I can get through it pretty quickly, then I'll probably start on Overflow. But yeah, I've been pretty successful in getting through these. I think the main thing is like all of the challenges in this section are the same kind of memory corruption issue, and they are building on top of each other in terms of just making the exploit a little bit more complicated each time. And so I am getting better and better at them with each one. I will probably go back to having a lot of difficulty when we get to format strings, and then again when we go to the next section. So my confidence is building, but I'm sure that will be knocked back down a little bit when I get to trying to exploit a completely different kind of challenge. I feel okay with the format strings one. I've watched like Live Overflow's video about doing it and have a decent understanding, but I don't think I've actually solved any challenges that were around that particular kind of vulnerability. So I'm sure it'll take me a while to get going on that. Okay, so we know the canary. So we can overflow the buffer as much as we want at this point, and we can control the return pointer because we can just make sure to write the canary in the proper location. So we can write 168 bytes of junk data, then we can write the canary, then we have 8 bytes of junk for the RBP value that was pushed. We don't care about that, I think. And then after that, we've got overflow to do our ROP chain, basically. And I am going to... So the problem with doing the ROP chain at this point is I don't know what the address of the libc stuff is. So I don't know what's in B4, or sorry, B0, which is the buffer. I don't know what goes into there prior to us printing stuff out, and I guess it is just other stuff that was on the stack. It makes it pretty difficult to know what to do. Is there a libc database online? I think there probably are, and there's tools for sort of doing what I think you're talking about inside of Pwn tools. In the previous walkthrough, they actually showed a neat technique. I didn't know about it at the time, but I will try to use it this time if I can manage to. They load the ELF binary for libc in the specific version that we have on our system. I happen to have the exact same version because I'm also on 1804. And then they can look up the address of any particular symbol for like the address of any function, for example. Unfortunately, so we know that this earlier program leaked the address of the printf function in libc. The reason that we needed the leak is because even though the address for printf inside of the libc file at this version is a fixed location, the libc file itself, to simplify, is put at a random spot in memory each time the program is run. So this is more like an offset that is fixed, but it's offsetting from a random base address. And so without the leak, I have no idea how to figure out what that base address actually is. And as far as I can tell, I don't have a leak of the I don't have a leak of a pointer to libc somewhere in this new challenge, in the one that I'm working on at the moment. It's possible that there is, and I haven't discovered what it is yet. So it could be in the data that we output if I just read the buffer without having written to it in the beginning. But that seems questionable. I don't know. I mean, I probably shouldn't discount it right off the bat. But it's also possible that we don't need to use any of libc. Even though we are in the dynamic section, I would think the idea is to return to and use gadgets from libc. I don't know. Maybe it's not libc, you know, maybe it's one of the other libraries that's used, like lib standard C++, which is where we have all of the symbols and instructions for the C++ code that it's using. Maybe there's an address from there somewhere that is gets printed out and or otherwise can be leaked to us. The only scenario that I can think of really is when we call the print number 2 option, review the food. When we what am I saying? Yeah, when we say print that buffer, which comes in and calls this bit of code right here, it calls puts, and we haven't yet written to that buffer, it has whatever data was already on the stack, and we can hopefully use that, but I would need to figure out what that is first. Oh, I've messed it up again. Okay. So what do I want to do? Well, I can look for gadgets in this program. Yeah, I always type no job. So we've got 49 gadgets. Probably not enough to do what we want to do. We can... I mean, it was enough to do what I did the last time. I think. No, because I was calling into libc to make that work. Okay. So maybe that first read is what we want to look at, in which case I'm going to run the program in GDB. No, that's not the way to do it. So we're going to run it. We are going to... am I already too far into the main function? Guess that's true. So I want to go into after that instruction, so like right here. So really? Okay. So we're in read. Guess this will be the one. You know, okay, that's one way we could potentially go about it. If we read to get the canary, so we do the stuff that we did just now to get the canary. Then we overflow the buffer even more. Overflow, so this is the buffer here. If we write all the way to the end and overflow to the first bit of the canary, then we can read the canary. Then on the second time, we overflow past the canary, past RBP, and then the data that we can read from it is, what am I saying? Is the return pointer. That return pointer is going to be a fixed offset into libc, because it's just go back to where we were in libc start main. And based on this address, we can see it's not part of the binary itself, it's part of libc. So, at least I think it's part of libc. It's in 7.6. Yeah, it's part of libc. Okay. So we can get the base address from that. There's always a potential that there'll be a null byte in that address, and then we have to like repeat this process a couple times to get past the null byte. But I'm gonna write it in a like, hopefully there's no null bytes kind of way first. See if that it happens to work. Okay. So the first thing we're gonna do is find the canary, because we need to keep that around. And then we're going to write again. So we'll write the input, and now we want to write, if we add 8 to this, we're at 76, and that'll go through the canary, and then another 8 be at 84. And the bytes beyond that, the next 8 bytes, or however many we have, should be okay. Let's make sure that, yeah, all right. And of course I'm receiving until, let's do it this way, just in the off chance that the canary or one of these addresses actually includes a new line byte, which is just a byte with value 10. So we know it's going to be new line followed by a sequence of hyphens, and if there's enough hyphens, just throw a couple more in there. I guess I can, is it the same? Okay. So it's very unlikely that we would, by coincidence, get an address that matched that. I mean, it's certain that we wouldn't get this as an address. We could, in theory, get it as a canary, and then even some of the address for the RBP that was pushed in would have dashes, but it's just very unlikely. So I'm not going to worry about it. But if we needed to put the full set of dashes that they actually print out, we could do that, I guess. But then it's just a, if that happens, that's a matter of rerunning the program and you'll get different random values and it won't trip it up multiple times, is my guess. So now we can read from 184 onwards. We want to read 8 bytes, hopefully, but probably not the full 8 bytes. Some of the top bytes are going to be null, and maybe some of the internal ones will be null, but we're not going to deal with that case right now. So 184 plus 8 is going to be 192. And then we can do ret adder bytes plus equals a null byte for n in len in 8 minus len ret adder bytes. Let's print out the hex of that address. It's not iterable, because we need range. Oops. Can't concat list 2 bytes. Okay, well, I'll just do a standard for loop, I guess. I thought I was going to be fancy with a little list comprehension, but who knows? Can't add bytes and lists of bytes, so fine. Okay, but it is backwards? Or what? It's too much? So we have 97 EB F8 D8 7F. I thought I said receive until, as in not including. Oh, keep ends equals false. How does receive until work? Drop equals true, I guess. Okay. That looks like it might be correct. Let's put that breakpoint on again, right? Or I guess we don't need to. Just look at this. So B97, all of these ended in B97, last 3 bytes. Okay, so these up here are randomized. Okay, so then if we know we're at 767, where do we go from here? 75 to 78. Okay, so this is the start of libc. So then we've got this address, and offset is there. Then you can do so that is our offset. From the beginning, from the base address of the libc 2.27 executable text segment, and so if we just subtract this number from whatever our return pointer was, then we will know the base address of libc, and we can use the one gadget thing to find the right gadget address offset from that base. Okay. So do like red adder offset is that. So then libc base is red adder minus red adder offset. And now we need to find the one gadget. Is it libc-2.27.so? Okay. Why am I doing it this way? I know it is in this location. So we need certain constraints. Stack plus 40 is 0. 40 hex rather. So that should be fine because we can write null bytes into where the stack pointer is, I think. Because it's going to do a read, so let us just go with this address. All right, so now we have the address for our gadget. Gadget is equal to libc base plus gadget offset. Okay, and now we want to write our payload. Which will include the canary. Let's see. Write the exploit input. Okay. I'm going to choose 1 again, and then can I just do the whole thing? I think so. We're going to do the whole thing with null bytes because stack pointer, which is wherever it was minus C0, we're going to add 40 to that. So we are at A0, I think. No, 90, which is going to be should be in the middle of this buffer, I think. If I am thinking about this correctly. Yeah. Okay, so if we put all nulls in there, then that'll satisfy the constraint that the gadget has, because it's going to reference that location and it's going to be a null for that thing. In theory, if we wanted to be really, if we needed to, I guess, we could know exactly where to write the data that was, I guess that would be pretty difficult because we would need to know, we would need to put an address there, not the string itself. So not going to worry about that. But I think if we have all nulls there, then we're fine. So that'll be our prefix. Then we need to send the canary. Then we send, say, null bytes for EBP, or RBP rather. Then we send our gadget. And I think we're good. And now we no longer choose to read the input, we choose to exit, which will return from the function. We should be good to go at that point. Ooh, definitely not. Definitely not. So choose 1, send all of this. You just say send line for the last one, I guess. Oh, you know what? We probably just need to like construct the whole payload together. That's fine. Kind of an ugly way to write it, but whatever. All right, what have I done there? Apparently you can't multi-line it. Well, let's try it all on one line and just live with that. And that worked. God damn. I'm mildly surprised that worked the first time I decided to try the exploit. Or, you know, once I say first time, like I didn't just fix 2 bugs in in the last 5 minutes, but my theory of how to do the exploit actually was correct, so that's pretty fucking sweet. Or, I mean, maybe they have a smarter way to do it in the walkthrough, so I'll glance through that. If I see anything that pops out as like they did a different thing, then I will review that, and, you know, we'll see if I could improve on this process. But this one was also nice. I mean, I guess maybe, you know, my opinion of a challenge really depends a lot on how quickly I'm able to solve it. But I think a challenge that includes a new concept, something that really does force me to think, like, how am I going to achieve this? Such as in this challenge, how am I going to get a pointer to libc? Where is that being leaked? Because the program is not just straight up printing it out as it did with the previous challenge, where it was just like, hey, here's the address of the printf function. That's why it's baby boy for that one, I guess, because they're just giving you the thing so that you can practice the concepts of using that to find the base address of libc, and then from there do, you know, a call to system or use the one gadget kind of approach, that kind of thing. And in this scenario, you have to think a little bit more. I did, at least. I had to think a little bit more to work out how could the pointer be leaked to us. And turns out, because we have a pointer to the address to return to when main is finished, and that address happens to be in the libc library, we can leak that in the same way that we leaked the canary. So yeah, I mean, this is, you know, the success that I've had on this one and the one just prior on this stream is really making me feel like a lot more confident about my ability to work on these pwnable challenges. Still quite a ways from getting, you know, real world pwnable. They're not called pwnables in the real world, I guess, but like real world exploits for some binary, the kind of thing that you would see in the like pwn to own competition. Those people are so impressive to me. I wonder what's happened, if they had one this year already or what. 2020, yeah, so they've already done theirs. I think it's towards the beginning of the year, like January or something. And the folks that I know that they work on these throughout the year and then just sort of deploy them, get them all working just right in the days of the competition in order to show it off. They're not actually like finding and working out the exploits in a 2 to 3 day time frame, but the exploits that they do have are always super impressive to me. And of course they make a lot of money. That's always nice. But an exploit that gives you RCE on Windows 10 from, I don't know, no-click or something is, here we go. We've got the 0-Day Initiative blog post, which will have the details, a little more of the details at least. Oh, these folks are from Georgia Tech. Lately, it's been a lot of like the big tech security companies from China have been the ones that are constantly winning over there. And like I think Tencent has a like security company and various stuff like that. So it's, it's interesting to see like just a university lab from the US. 6 bug chain, right? So this is like the kind of thing that is really, levels beyond what I'm working on now. Even one of those bugs is probably significantly more involved than what I'm working on, because the software wasn't written with being exploited in mind. But you weren't just doing one of them. They had to do 6 different vulnerabilities, like binary vulnerability exploits, and chain those together in order to get remote code execution and root escalation in from Safari, basically. So I guess maybe this is a exploit where you go to some website and it sends the right malicious JavaScript or combination of JavaScript, CSS, HTML, whatever it sends to your browser, that Safari gets exploited. Then you have remote code execution, and then they have an escalation to root privileges. So, I mean, in terms of the value of this kind of real world exploit, or not value, but just this is the sort of thing that everybody thinks about when they think about a hacker who's just like, they send you a URL and suddenly they have control over your computer. There's a lot of hacking that goes on that's not nearly that involved, and it's just really difficult to accomplish that these days because browsers are so locked down and there's so much work put into securing them. But with enough effort, you can come up with a sequence of 6 different bugs that you all, put together just right to enable, getting past all of those security measures. And then there's a privilege escalation that I guess just one person worked on. Like, I mean, that's pretty fucking sweet that this guy got $40,000 for throwing that privilege escalation in there. People have definitely made a decent point about the morality of, like, they didn't discover the privilege escalation exploit that day. They had it in their pocket sometime probably throughout the year and said, oh, if I hold on to this and then I and then I show it off at Pwn to Own, which is, the results of what they're doing are not actually public. They are given to Microsoft in this case, or Apple, or whoever the software developer are, so that they can fix those before the announcement is made of the details of the exploit. So technically it fits within the realm of like responsible disclosure, but they could have disclosed it months and months ago when they first discovered it. Instead, they decided, I'm going to hold on to it to wait for this competition in March and get myself $40,000. So it's a little bit, on the it's more questionable than if they had just written it to Microsoft and gotten like a kudos and maybe $1,000 or something. I don't know. Assuming that Microsoft had has a decent bug bounty system or program in place. I assume they do, but in any event, they were able to get $40,000 out of it doing this competition. And that's, if I was in the position to do that, I would be very happy for that kind of money. it would go a long way to letting me work on more hacking stuff without having to, have a full-time job. So good on them for getting it. And then another guy working individually who's on a CTF team got 30,000 for an Ubuntu privilege escalation. That's pretty sweet. And maybe some of these are the kind that I don't know what the bug bounty system or program is for Ubuntu. Like maybe they don't pay very much for that from Ubuntu, so the holding out for the 30,000 from the 0 Day initiative is the way to go. I don't know. These guys, fluoroacetate, are really cool to me. Amat Kama, he was on this YouTube channel that I haven't kept up with it very recently, but there's basically a really small scene of competitive Ponables challenges. I guess they haven't done any in the last couple weeks, or last couple months rather. But these were like head-to-head 3 or 4 hackers that do this sort of binary exploitation work are given the same binary, and then they race to see who figures out, who reverses it and gets the exploit going the first, basically, right? So it's pony racing, as they say in the name. So these are always really cool. He was on it. He did incredibly well, which is understandable because, I think if you're winning Pwn to Own, and I think he's been master of Pwn a couple times, or at least this team that is fluoroacetate, they have, and they got master of Pwn on 2020 as well. I didn't go through the full list, but they've probably got more stuff in the later days and ended up with the most points, basically, for the combined set of all the exploits that 0 days that they basically were able to get working and then, tell the vendors about during that competition. So it's just incredibly impressive, the work that they do. And that's sort of like what I aspire to, in essence, to be able to have skills even vaguely in that range. But that is a long way from where I'm at, for sure, doing these CTF challenges right now. So if I just keep at it, do something every day, maybe I will be able to get there eventually. Okay, so I'm gonna skim through the walkthrough real quick, and I'm not gonna read it word for word as I had been doing in the previous ones, because I think that just is kind of a drag. But if I see something in it that I didn't expect to see, that wasn't how I went about it, then I'll dig into that for sure. They get the stuff from Ghidra. I mean end of input or something, I don't know. Oh, B8, not 08. Okay, yeah. They're doing 68B00, which is, yeah, the same executable region for the libc. I mean, what they're talking about in here seems like they're going in a different direction from how I went about it. So now I'm curious for sure. So they are saying, looking at the imported functions in Ghidra, we can see that puts is an imported function. Puts will print the data pointed to by a pointer it is handed until it reaches a null byte. The GOT table is a section of memory in the ELF that holds various libc addresses. It does this so the binary knows where it can find those addresses, since it doesn't know what they will be when it is compiled. Since PIE is disabled, the GOT entry addresses aren't randomized, and we know what they are. If we were to pass the GOT entry address for puts to puts, which we can call since it is an imported function, meaning it is compiled into the binary, and we know its address because there is no PIE, we will get the libc address of puts. Also a quick tangent. So maybe they're going to return to the puts function and have it print puts as well. I don't know how you return to the puts function if you don't know the base address of libc. So, gonna keep reading, but this is definitely not, I didn't do anything with puts or any other libc function directly. Okay. Also a quick tangent, PIE essentially means that there's ASLR for addresses in the ELF. For this binary, that would include these regions. If this was enabled and we wanted to do what we were doing with the puts info leak, we would need another info leak in this region. Yeah, that's also true. Well, oh, I see. They are returning to the function in the like procedure linkage table or something, or yeah. Okay, so they're finding the put symbol from the binary, not from the libc, which will give the address of the PLT function that ends up going to puts. And they also have the GOT entry location. So, okay. And then they're going to build a ROP chain. Let's look at their exploit. I feel like the way they went about it is more complicated than what I did, it feels like. But if I could not overflow my buffer to the point where I could start reading the return pointer that was originally in place when the main function was called, and is pretty much and is guaranteed to be a fixed location within the libc executable memory segment. If I couldn't actually leak that address, then this approach would work, because as long as the binary itself is not PIE, not the libraries it's using, but in this case the SVC binary, if it is not compiled as a PIE executable, then we can do this global offset table PLT work and come up with appropriate offsets. They didn't use the one gadget approach, but they probably could have. Maybe, I think they did this one at the time. So this is like the write-up from the author of this course, and they probably did this one in 2017, and either the one gadget library didn't exist in 2017 or they just didn't know about it, but they're not using it in this one. However, in the 2019 one, they did use it. So at some point in between those 2 years for the Seesaw competition, they learned about and started using the one gadget tool and that technique rather than return to system, as it looks like they're probably doing because of the offsets that they have. So let's see. Right, so they put the global offset table address, or they put a pointer to the global offset table address for puts into RDI, and then call the PLT function, a little stub for puts. So then it runs puts, uses RDI as a pointer to something, and prints out the bytes for that are whatever is actually inside of the data at the GOT address. So now they have the address of the puts function in libc that has been printed, at least. I think the thing is they exit the okay, and then to avoid actually quitting out of the program when they try to exit out of the loop, they go ahead and also put in the address at the beginning of main. So when they hit the leave call, where they put in menu option 3, which would normally quit out of the program, main function returns, but it returns right back to the beginning of main. So now they have access to continue through again, because they've already overwritten the return pointer for main once with their ROP chain. So they basically are doing 2 separate ROP chains, once to do the leak for libc, and then a second time to do the actual pop into the shell. Okay. That is a useful technique, I would say, because the approach that I used is less guaranteed to be available. You know, maybe you could do an overwrite that allows you to leak the canary, and well, no, I think in my case, if you can, maybe the canary gets leaked some other way, so you don't have a like just puts the whole buffer, but you can still overwrite the return address. There's definitely like circumstances where my approach I don't think would be possible, but this approach would be possible. So it is good to know that, let's say. Yeah, cool. I'm glad that I got another mechanism to put in my list of things to try in the upcoming ones. I think I feel like I've gone long enough on this stream, so tomorrow I'm going to try to tackle these next 2, the final 2 in the stack buffer overflows category. They're both still in the dynamic section, so it's the same theme of using gadgets from libc, and you know, maybe we can just do the one gadget thing again. Maybe we have to build a ROP chain that's a little more involved. We'll find out when we get there, but most likely we're dealing with some amount of needing to leak the libc pointer, or a pointer inside of libc, so that an address inside of libc, so that we can figure out the base address that it has been loaded at, and then do, you know, the same shenanigans basically that we've done in the last 2, the 2 that were on this stream. So since this went pretty well, I feel mildly confident about getting through the last 2 as well. They don't name it, but I feel like the HS CTF is the high school CTF. Let's do a quick search. Maybe it's a different one called HSCTF. Does that help at all? I don't know how to find this particular. I called it story time, right? Yeah. I don't know how to search for this, frankly. Given that they didn't expand on what that acronym stands for, it's, you know, if it were the high school CTF, I would expect it to be easier than some of the other ones, because in my recollection, I mean, maybe I have come to the wrong conclusion about high school CTF, but I thought that a lot of the challenges were even more beginner oriented than the ones that I've been working through. And just, you know, understandably, I mean, if you're targeting high school students, they will have had less time to get familiar with this stuff and get the experience. So I don't know, but if I can work out where that challenge is from, then I'll know if it's the high school one or not. Okay, that's everything for this stream. As always, you can go to if you want to contact me, you can go to my website. It's hamled.dev. That will, for now, just redirect you to my GitHub page. And that has my email address on it if you like. I guess I can throw my Twitter on here as well, so that I don't have to keep also going to my Twitter account. But if you want to reach out to me on Twitter, you can do that at hamled online. And, you know, just send me a tweet or follow or whatever works for you. And I'll try to follow you back if you want to follow me. So, cool. Thank you for watching. If you're still watching Meowcat, thank you for sticking it out. Hopefully some of this has been interesting or informative for you. And if I have some time to hop on like Ash Fox's stream and see what he's up to today, or later, it'll be like evening for him or something, I don't know. Then maybe I'll see you there. All right, adios.